Okay, I think that's recording now. So we're starting chapter 11, statistics. Can you make sure that you read this green box with terms defined? This is on page 284. Data, I think that's self-explanatory. Categorical versus numerical. So categorical is basically worded data, or if you do science, you'll know the difference between qualitative and quantitative. So the categorical is the qualitative, like do you feel happy or sad or something, as opposed to qualitative would be how happy do you feel on this scale of 0 to 5, 1, 2, 3, 4, or 5, which brings us to numerical. Within numerical, there's two types, discrete and continuous, and that's where the questions will start. I think numerical data is self-explanatory, as in how many pairs of shoes do you own? One, for example. Okay, population versus sample. So population is the entire population that you're interested in. So if I'm interested in knowing something about Australians, I could survey the entire population of Australia. That would be called a census, right? They've got census under. So that would be the actual census is the actual survey of the entire population, right? As opposed to taking a sample, where you're just maybe surveying 100 people or 1,000 people, right? Or whatever you can get your hands on. If you're at university, a lot of PhD students doing these types of studies on fairly small samples, 20, 30 people. Parameter. So this is a statistical, something like an average or a standard deviation, some statistical parameter. They say quantity, but parameter strictly refers to the population. So if I said this mean is a parameter, I mean it's the mean for the entire population. Survey is the actual information from the sample. A statistic, so this is coming from the sample. All right, so compare statistic to parameter. Right, statistic and parameter, same thing in terms of, if I'm looking at means, medians, modes, ranges, standard deviations, whatever the actual quantity is, it's the same, but a statistic comes from a small sample and a parameter comes from an entire large population, right? The distribution of the data, you'll need to know these. Symmetrical, positively skewed, negatively skewed. You'll be looking at that in the questions. Here the mean and median's right in the middle and you're just symmetrical. So this is for numerical data, right? Positively skewed, there'll be a few numbers that are large that are skewing the data out to the right or positively. Whereas with negatively skewed data, there's a few numbers that are much smaller than the others, giving this negative skew. Every now and then there's an outlier which is very different to the other set of data. You should always include your outliers, and the book does say this. Data values that are much too large or much smaller are called outliers. However, they should be included unless you know that something's gone wrong when you got that information. So if you're doing a scientific experiment and you get an unusual data which lies, get some, I don't know, force reading or temperature or some numerical data, and it's a lot different from what you think it will be, too bad. You don't get to just ignore it, right? Unless you know something went wrong with that experiment. So hopefully the language of statistics is fine, and you've seen some of these words before. Okay. Now we'll just run through, what have they got here? I want to run through discrete continuous. Okay, so it's in the green boxes. So when it comes to numerical data, which is what we're interested in mathematics most of the time, and even if we do a survey and the results are quantitative, the information is often converted into numerical. So earlier on I said, imagine you had to rate your happiness from 0 to 5, where, I don't know, 5 is very happy, 4 is moderately happy, 3 is in the middle, so it's neither happy nor, you get the idea. We've all seen those types of surveys. Well, that's a way to take something quantitative, like trying to measure happiness, which is actually ridiculously difficult to do, because who even can define happiness accurately in a scientific setting. But anyway, this is what happens out there in the world. They will take quantitative data and they will actually turn it into numerical data, right? So this is often how studies are done. It allows for high volumes of survey participants. What's the word? It allows you to survey lots and lots of people, right? Because the other option is to interview people one-on-one, and you can get very good information by doing that, but it's maybe not as impressive in our current research system that sort of rewards mathematical analysis and high volumes of research papers. Anywho, you don't have to worry about that unless you end up doing research at university or in a private company. So what you do need to worry about is, can you spot discrete data or continuous numerical data? And it's quite easy to do. So discrete, as the word suggests, this is numbers, usually whole numbers, but not always. It just means the numbers are coming in particular values, and they cannot exist in between those values. It's like shoe sizes. I can have a 9.5 shoe, but I can't have a 9.1327 shoe, right? As opposed to continuous variables which exist on this continuum, and this, even though they will have an upper and a lower limit. Right? So say we're talking about the heights of human beings, there's some smallest height, there's some maximum possible height a human could ever be, but in between there is potentially infinite possibilities, right? Just depends how accurately I can measure. Right? So discrete is, you can think, do I count this? This is how you can identify, for example, the number of people or a score out of 20. Is it something I could count? Continuous, it's, do I need to measure it? Heights, weights, speeds, and time as well. So when we get to those questions, yada, 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 I'm going to do histograms in another video. Just want to get you started here. All right, so we're looking at 11A. Now I'm going to get a pen and write the answers on the thing here. Yep. Discrete versus continuous, number of students. All right, you cannot get 1.375 of a student. They come in ones, twos, threes, right? This is definitely discrete. You would count them up. The weights of cows, that's something you would have to measure. The possibilities are endless, even though they would exist within a certain range. They belong on this continuum. So this is continuous. I might just write cont because it's quicker. The maximum temperature of a city, I assume they mean like ongoing, let's just say it's continuous. Temperature's continuous, you've got to measure it. Yeah, okay. The number of hairs on a head is discrete, but it's a bit of an odd example. All right. The scores obtained by a gymnast. The individual scores are continuous, yeah. Discrete. And the amount of water you consume every day is continuous because it would be a volume that you would measure, and it could differ by very small amounts. Okay, if we go down, I'll just erase that. I just want to check if there's any more of these discrete continuous questions. Consider, it won't let me scroll down, sorry. Oh, okay, here we go. So the age, I can just talk these to you. His age is 28. Now, if we measure that in years, we could say it was discrete. If we were measuring it, it's kind of a weird one, isn't it? If I'm measuring time, I would say it was continuous because time exists on this continuum. But I think if we say we're just going year by year, we'd say age is discrete. Height is definitely continuous. Age, I'm not so sure about. You could see what it says in the answers. Just be aware that time is continuous. I would say number of years is discrete. Height is continuous. Tournament wins is discrete. Serving speed, it's been averaged. I guess it doesn't matter. We'll say that that's continuous. Ranking 6, that's discrete. Career prize money, it is discrete money, but you almost want to say it's continuous in this day and age where you have many decimal places. But at the end of the day, you're going to come to some dollar amount, and that's where I'm getting the discrete from there. Now, when it comes to some of these ones that might be, you stop and think about it a bit, and it's a bit confusing. It's interesting to think that sometimes we can think of things that are, we're defining things as continuous, but in different contexts, maybe they're discrete. And the example that's coming to my head is something like number of atoms in chemistry, even though Avogadro's number is only known to 9 significant digits. So this science can't do this yet, but potentially we could count the number of atoms in a substance and turn something that was continuous into something that was discrete. So sometimes if you think about these, overthink it, or if you're looking at the information in a different context, the border between discrete and continuous becomes a bit fuzzy, right? So, I mean, that's typical of a lot of our concepts. There can be a fuzzy border between them, even with money. So I'm fairly sure, I'm just looking up in the book now, I'm fairly sure money, yeah, here it is, that say prize money is discrete, like I said, but on the stock market or in a bank and you see the decimal places whirring, past, you think, oh, it sort of looks continuous. Or an example of height here in centimeters, right? Well, centimeters I could think of as being discrete if we're rounding to a centimeter, right? But the book, and like I said this as well, the book says it's continuous, right? Because we could be in between those centimeters. We could be anywhere in between, potentially, right? But if I was to start rounding to the nearest centimeter, then at that point, I've made this data discrete. So it can be a little bit confusing, but the type of question you would get, I think, would be fairly clear. And what you need to remember is, do I count this or do I measure it? So counting discrete, measuring continuous.